Hello everyone, welcome to my videos on elementary differential equations. This is video number 18 for chapter 5, and the topic for the chapter is the Laplace transform. In this video, we will prove the convolution theorem and then we'll take some examples. Let's begin with the proof. So let's first repeat the statement of the theorem. It says that if capital F is the Laplace transform of the little f and capital G is the Laplace transform of the little g, and then if you want to find the inverse Laplace transform of capital F times g, and it equals to the convolution of f with g, which is defined as this integral from 0 to t, f of t minus tau times g of tau d tau. Okay, and this holds when the integral exists. Okay, let's now provide a proof for that. So in the definition of the theorem, we know that capital F and capital G are Laplace transforms of the function little f and little g. So let's write out. Then this means capital F of s equals to this integral, where we call the integration variable psi. Okay, you can call it anything, but we'll call psi because it will be convenient. And then gs, then this is the Laplace transform of g of t, and then this is an integral like that, where we use tau as the integration variable. And then we see that capital F times capital G now simply equals to this integral here, which is capital F, times this integral here, which is just capital G of s. Then we can rewrite the product of the two integral into the integral of the product, because this integral here, okay, so actually it's this one I manipulated. So this integral here in the end is a function of s. It doesn't have anything to do with tau. So with respect to this integral, the value here would be a constant. And then we can move it into the integral, and it will be treated as a constant. So now we'll have a double integral written in this specific way, where the integration variables are psi here and then tau for the outer integral. Okay, and the next step is then we would move this term with the exponential function e to the negative st, and then this is constant for this integral, so we can move it inside. Okay, and then we have that where this term comes from here. And then we can combine the two exponential functions here into e to the negative s of tau plus psi. Okay, and now we make a variable change. So for any fixed tau, we call that psi minus tau equals t. Okay, and with this variable change, then we know dt equals to d psi, and when psi is 0, we have t equals tau. Then we can rewrite the integral and the internal integral here into integrating from tau to infinity e to the negative st f of t minus tau dt. And now, since g of tau doesn't have anything to do with t, which is the integration variable here, so it's treated as a constant for this integral, and therefore we can move it in, and then we can write it like this. Okay? So we see now we have a double integral, and what is in here looks already very familiar to the convolution function. Not not yet, okay? And but the integrations from 0 to infinity in tau, and then inside in the integrand we have another integral from tau to infinity dt. Now let's look at the integration domain formed by the two variables t and tau. We see that it's not the whole two-dimensional space, it's only part of it. So let's look at the d tau. Tau runs from 0 to plus infinity, so as tau goes from 0 to plus infinity, the t would take only the part from tau to plus infinity. So let this be the line t equals tau, and then the t will take the value from tau to infinity, and therefore this 45-degree wedge starting from the origin going up to outside to infinity, that will be the integration domain. And then one can switch the order of integration and write the integral in a different way. Okay, so let's say if we move t to be the outer integral, so let t run from 0 to infinity, and then for every given t, what is the tau value? And the tau value will be from 0 to t. Therefore, we have this change of order of integration. This integral here from 0 to infinity d tau, and then tau to infinity dt is the same as 0 to infinity dt, and from 0 to t d tau, because we can see from this graph that it's the same integration domain for both double integrals. Okay, now let's switch this order of integration and we can write the following. So the right hand side now, we just switched the order, and then we put still the whole function here, we didn't touch it. And then we see that in this integral, it's integrating in d tau now, and this function, exponential function here, is only a function of t. It does not depend on tau, so it's a constant with respect to this variable. Therefore, we can move it outside the integral, and then we can just integrate this and then multiply with the exponential function. Now we see that the integral here in the bracket is exactly the convolution integral. It's f convolute g of t. And this function is multiplied by this exponential function and then integrated in dt. Okay, so now we recognize this integral is exactly the Laplace transform of the function here, f convolute g. Okay, and therefore we can write that's the Laplace transform of f convolute g, which means f convolute g is the inverse Laplace transform of capital F times capital G, which is exactly the statement of the convolution theory. Therefore, we completed the proof. Okay, so the convolution theorem states the result of the inverse Laplace transform of the product of two functions. And then based on that, immediately one can extend this to multiple convolutions. So let's say we have n functions f1, f2 to fn, and their corresponding Laplace transform is capital F1, capital F2, and capital Fn. Then the Laplace transform of the convolution of all these functions will equal to the product of their transforms. Okay, so let's take an example of some straightforward application of the convolution theorem. Let's say example 1, we want to find the Laplace inverse transform of this function, capital H of s. Of course, there are different ways of doing this. We can use partial fraction and take inverse transform of each term. And we can also recognize that the hs here is a product of two functions f and g. If we break the denominators into two terms, so f will be 1 over s squared, and g is a over s squared plus a squared. Okay, we see now for these two functions, their inverse Laplace transform is quickly obtained. Then, to find the inverse transform of their product, we can apply the convolution theorem. So this offers an alternative way of finding a Laplace inverse transform. Okay, so we see that the inverse transform of capital Fs is f of t is t, and then for the g of s, the gt is just sine of at. Now we can use the convolution theorem and compute the inverse Laplace transform as the convolution of little f with g. And let's put in, so the little f is t minus tau, f of t, and evaluate at the t minus tau, and then the sine of a times tau d tau. Okay, so it's a bit of a work to work out this integral, and if you work it out, so I skip the details, if you work it out, and then that is what you will get. Okay, so let's take another example of applying it into the initial value problem. So let's say we have a problem, y prime is ay plus gt, where a is a constant. The initial condition is y0 is given as y0. We know that this is a first order linear equation. We can solve it by the method of integrating factors, where we see that the integrating factor is, we call it mu. Here would be e to the negative at. If I multiply that on the equation, then the first two terms becomes a derivative, mu times y, and then I'll have mu t times gt. Okay, put in the mu, which is e to the negative at, then I have this, the derivative is the mu e to the negative at times gt. And now we can integrate both sides from 0 to t, from 0 to t, from 0 to t, the left and the right. And we see the left, you're integrating an integral, so you just need to evaluate it at the two end points, which we do here. And then here is e to the 0, which is 1, so it's just y naught. Okay, and the right hand side is not changed. Yeah, and then we can move this to the right hand side and then move this to the right hand side and solve for yt. Okay, so if we do that, you move the y naught to the right hand side and then you multiply both sides by e to the at. Okay, and then we can distribute e to the at to two terms, and let's take this first. So we get this term, and then we have e to the at on this integral, where we can move it inside because it's a constant for the integration. And then we see that these two terms, we can combine them together. We'll have e to the power t minus tau. Okay, so then this expression looks very interesting. It's an integral of a product of two functions, one evaluated at tau, the other evaluated at t minus tau. And that very much reminds us of a convolution. So in fact, so this integral is the convolution of the exponential function with the g. Okay, so an interesting observation is that let's now take the Laplace transform of yt and using this expression. Okay, so the transform of the first term, take y naught as a constant outside, and then we do the Laplace transform of this convolution, and then that is the Laplace transform of each term, and then multiply. And that's according to the convolution theorem. Okay, and then this transform, and Laplace transform is 1 over s minus a, and then multiply by y naught. And then here, the Laplace transform of g is g of s, and then it's multiplied by that is again 1 over s minus a. Okay, so now let's compare this to the other standard way that we used to do. So we can take Laplace transform directly on the differential equation, and then we will get sys minus initial condition y naught and equal to a times ys plus g of s, right? And then moving the y naught to the right hand side and the ys to the left hand side, you can solve this algebraic equation of capital Y of s, and you will get y naught plus g over s minus a, which is exactly the same result as we get by finding the solution and then take the Laplace transform. So of course that's no surprise, but the interesting thing is that here we end up with a convolution, and we can apply the convolution theorem. Let's take one more example. Probably is the most interesting one. Okay, so let's consider a second order equation. So a u double prime plus b u prime plus cu equal delta t. Remember, that's the impulse function. Okay, and initial conditions are 0. So u0 0, u prime 0 is 0. Now let's call this equation and label it. That's equation A. This is the homogeneous initial condition with impulse function as a source term. That's the equation. Now let's try to solve this. So we can take Laplace transform of both sides. Let capital U over s be the Laplace transform of the little u of t. And then we'll have the following. So we'll have a times s squared for the double derivative, u, plus b times s for the first derivative, u, plus c times u equal the Laplace transform of delta is 1. And then we have no initial data terms because they're all 0. So we just have that 1. And then we see the left hand side, you can take out us as the common factor, and what you have remain is exactly the characteristic equation. Okay, so we have u of s is 1 over the characteristic polynomial. And now let's consider a more general equation, which let's use y as its unknown. As you see, the left hand side is the same as a, and then it equals to some function g of t, not just delta here. And then initial condition is not 0, so y0 is y naught, y prime 0 is y naught prime, so they don't have to be 0. Let's call this b. Okay, so let's try to solve this and take Laplace transform on both sides, and we see we'll have the part that's the characteristic polynomial times y of s, and then we'll have the terms coming from the initial conditions because they're not 0. Okay, then we'll have as plus b times y naught minus a y naught prime equal gs. Now we can move these terms to the right hand side and solve for y of s. Okay, so we see that we'll have this part moved to the right hand side, which is here, divided by the characteristic polynomial. That's the first part of the solution, and the second part is this g of s divided by that polynomial. Okay, so we see that from this form very clearly that this first term is caused by non-zero initial conditions, and the second term is caused by the source term here. Okay, so let's define these two functions. So for this function, we call it capital phi of s, and then this function, let's call it capital psi of s. Okay, let's see now. We're taking inverse Laplace transform. So let's say yt equal to little phi of t plus little psi of t. where the little phi of t is the inverse transform of capital phi of s, and the little psi of t is the inverse transform of capital psi of s. Yeah. So we see phi of t is the solution caused by the non-zero initial condition, and psi of t is the source term, trigger the system to respond. Now let's look at the response term, the capital psi of s. We see that we can write it into two terms. One is a capital U of s, which is the solution for the problem A, which is 1 over the characteristic polynomial, and then G of s, which is the Laplace transform of gt. So this function u is important here. It is known as the transfer function. Okay, so now we can apply the convolution theorem. So for the inverse transform of capital psi of s, we can compute it as the convolution of u with g. Okay, and u is the solution of problem A, and which is the integral from 0 to t of u of t minus tau times g of tau d tau. And that one gives you the solution for general force function of g. Okay, and yeah, so you see that if you know the solution with the impulse source term, then you can compute the convolution of the impulse with the actual force term you have on the right hand side, and that will give you the corresponding system response part for your equation. Well, okay, so that's the last example, and that's all I want to say on convolution. And also this is the last video for chapter 5, and next time we'll move on to a new chapter. So I hope you enjoyed these videos so far, and I look forward to seeing you next time.